This is a lecture on Chapter 8, Weathering Soil Mass Movement. So this lecture covers three main topics: weathering, mass wasting, and erosion. I know it's hard to see in this image here, but weathering is the disintegration of rock and its decomposition at the Earth's surface. So if we have exposed rock over here, it's going to go through sleet, rain, snow, all different types of weathering processes to break that rock up into smaller pieces. Mass wasting is the transfer of that rock material down slope under the influence of gravity. And then erosion occurs that incorporates an agent moving these really smaller, much smaller sediment size and particles. Typically water, but it can be wind, or glaciers can move these smaller sediments to different areas on Earth's surface. So let's talk about weathering first. See this boulder right here, this erratic? This was split open by a weathering process we call mechanical weathering. That's the breaking of rock into smaller and smaller pieces. This is pretty intense. I mean, what happens here is when you have, in really cold areas, you have ice. So if it ever rains here, water will infiltrate into these small little cracks. And then when overnight temperatures drop below freezing, water expands by volume. So it'll actually force cracks open in rocks like this. Another type of weathering is chemical weathering. And this is the transformation of minerals within the rock to new and more stable minerals. Okay, so these processes work simultaneously. So let's pretend, and they actually help each other out. They kind of accelerate the weathering process once you get some mechanical weathering in it. But let's pretend we have this cube of granite. It's exposed at the Earth's surface, and you can calculate the surface area that's exposed to the elements, to rain, to wind, abrasion, and all that, all those weathering processes. And when it's one big block like this, it has 24 square units. But if you have mechanical weathering starting to like break it apart into smaller pieces, now all of a sudden its surface area increases by almost by twice the amount. And that's because, see, these interior surfaces are now exposed to chemical attack. So that's what happens with weathering. Mechanical weathering will break rock into smaller and smaller pieces, and this exposes even more surface area for chemical weathering to take its role, and so it accelerates the process. So there's four important mechanical weathering processes. One is frost wedging, which I mentioned before, and that's the expansion of freezing water. I know you've probably done this by accident, like maybe you threw in a drink into the freezer, you know, being like, all right, I just wanted to get it cold real quick, and then you forget about it, and then you go back to check, and the drink has exploded or expanded and broke the bottle. And that's because water, when it goes from its liquid to solid phase, expands in volume by like 9%. So especially if you have a glass bottle, that could be a big mess in your freezer. Salt crystal growth is the same idea. When you go to coastal areas, let's pretend there's a coastal areas and there's waves crashing over here. There's a lot of salt spray, and that salt spray comes and coats coastal rocks. And when that water evaporates away, it leaves behind salt. And that water can kind of infiltrate into the cracks of rocks. And then as salt crystallizes, it can expand those cracks. Then there's sheeting. Sheeting is like layers of granite that kind of exfoliate outwards because of the lack of pressure. And it resembles a lot like an onion. You know how onions kind of come off in layers. And the last example is biological activity. Here you have a tree growing directly on this rock, and its roots are kind of forcing its way into the cracks and crevices of the rock and breaking it apart. So those are all mechanical weathering processes. Here's just the visualization of frost wedging. So in these cracks, which would represent rocks kind of exposed at the Earth's surface over here, it'll rain, sleet, snow. So water gets in these little crevices and pore spaces and cracks, and then overnight it freezes, it expands, and then it forces rocks off. That's where you have falling rocks pile up in this talus slopes at the bottom of rock exposures near mountains. So that's frost wedging. Here's the visualization for sheeting. Okay, here's the half dome at Yosemite National Park. And it's an intrusive igneous rock, meaning that it crystallized deep underground, kilometers underground. And as it crystallized, it was under a lot of confining pressure. But now, over millions of years of erosion and uplift, these intrusive igneous rocks that were once deep underground are exposed at the surface. And because there's nothing on top of it, there's no pressure or confining pressure, the rocks begin to expand. And as they expand, they can form these kind of sheets. If you look at it closely, it almost looks like peeling skin or exfoliating skin. Joints can form this in this fashion as well. All right, chemical weathering. This is where water plays a role in adding or removing elements and actually altering the minerals within the rocks. Water is the most important agent. Water has oxygen in it, so dissolved oxygen in water oxidizes a lot of the minerals and materials. Carbon dioxide also plays a role. That dissolves in water and forms carbonic acid, and that's slightly acidic, and that can also alter a lot of rock material on the Earth's surface. So let's take granite, for example, very common intrusive igneous rock. And granites have a lot of potassium feldspar. And potassium feldspar is susceptible to chemical weathering. And so when it is exposed to precipitation, it can slowly produce clay minerals and soluble salt or potassium bicarbonate, and then silica in solution. Quartz in granite is very stable, meaning that it's very weather resistant. So it remains kind of unaltered. And this is why quartz kind of breaks down perhaps into smaller pieces because of mechanical weathering and eventually becomes sand. And that's why a lot of our beaches in the state of Florida are mainly composed of quartz. And then all the other silica minerals we've talked about, they'll produce insoluble iron oxides and other clay minerals. So here's the breakdown. Quartz, really residual, just becomes quartz grains. A little bit of silica releases out into solution. Feldspars break down into clay minerals, plus this material goes into the kind of groundwater system. And then amphibole and olivine, so your more ferromagnesium minerals, will break down into clay and iron oxides. So a lot of oxidation occurring. Another type of chemical weathering is called spheroidal weathering. This generates rounded rocks, and you see this in Joshua Tree Park, California, really hot, dry desert area. And this happens over time. You have exposed bedrock, in this case it's sandstone, and water penetrates the jointed rock, right? So mostly initially kind of like a physical or a mechanical weathering process. And then chemical weathering does its bidding and then starts to round the edges of the exposures until they become completely round here, right? Don't believe the History Channel, man, aliens. No, it's a geologic process. Okay, so when you have a lot of mechanical weathering, that aids chemical weathering, like we talked about before, breaking it down to smaller pieces, and because of that, increasing surface area. But there are a lot of important factors that affect how fast things weather. One is the mineral composition. Okay, some minerals are more susceptible to weathering than others. Calcite in limestone is very susceptible to weathering. It's very soft, so like say you had marble, that would weather very easily. Potassium feldspar weathers easily. Other minerals like quartz don't weather as much. And then also, the rock itself, if it has a lot of physical features like joints or expansion cracks, that will accelerate the process of weathering. So have you guys thought about your tombstones? I know, maybe you're not thinking about that or haven't planned for it, but everyone goes to the grave, right? And that's what's the guarantees in life. You're going to die and you have to pay taxes. Well, when you you know, at some point in your life, you may, I don't know, maybe you want to get cremated. I don't know. Maybe you want to be buried in a cemetery. But so if you want to, if you're going to get buried in a cemetery, choose your headstones wisely. Okay. This is a granite with a limited amount of feldspar in it. And this was erected in 1868, and we can still read who this person was, 1801 to 1868. Peter Sweat, I'm guessing, that's how you pronounce his name? Anyways, someone went all fancy and chose marble for their headstone, and they died after Peter Sweat, 4 years afterwards. But can you even read this? Who is this? I don't even know. What does that say? Ted? I don't know. Roosevelt? I don't know. So this marble headstone has weathered away because it's made of marble. It's made of calcite, a mineral called calcite, which is very susceptible to weathering. So yeah, choose your headstones wisely, guys. All right, so the rates of weathering really are dependent on a few factors. The most important is climate. If you have a moist and warm environment, Florida, those are crucial. Chemical weathering is the most effective in those types of environments. And so differential weathering occurs when you have rocks exposed at the surface that may be composed of different minerals, and some of those minerals or rock units will weather out faster than others, and so we call that differential weathering, meaning like different rock units will weather at different rates, some faster, some slower. And what ends up happening is it causes pretty unusual and spectacular rock formations and landforms, kind of like, the old cover of the book had the arches from Arches National Park. Or, maybe you've seen this. Red Dead Redemption kind of based their landscape on real locations out west. Also, you could see these, almost these mushroom-shaped features. Don't push them over. They take thousands of years to form. You can get arrested for it, too. But yeah, so this process and this unusual alien landscape is produced by differential weathering. All right, let's jump to soil. Soil is interesting because it's kind of like an interface between different Earth systems. So we have the geosphere and rocks, right? Those are inanimate, like non-living things. And then we have, on the other end, organisms. And rocks break down slowly into regolith that eventually becomes soil. And then organisms grow out of the soil. And then we eat either, things that grow from the soil or the organisms that eat the things that grow from the soil. Wow, long story short, soil connects the kind of geosphere to the biosphere. Okay. And what soil is a combination of mineral matter, water, air, and humus, which is, I forgot to put that in there, that's organic material. Okay. And so when rocks break down into smaller pieces, that becomes regolith. Those are rock and mineral fragments, and that supports the growth of plants. This is the only GIF I could find of soil. That's a very mulchy soil, so not a great example. But here you go. This is much better. This is mostly mineral matter. Okay, we got some organic matter, which is good. That's called humus, water, and air. That's what makes up soil. So soil has texture. I don't know if you noticed this, but it's made up. The texture refers to the proportions of the particle sizes. So sand is the largest. This is kind of a review from sedimentary rocks. Then silt is smaller than that, and then clay is the smallest. So all soil is made up of these three, or proportions of these three particle sizes. And most soils are considered a loam, which is a mix of all three. So it have like maybe 10% clay, 20% silt, and 70% sand would be a loam. And that'd be a sandy loam. Okay. And this texture diagram helps describe all the different soils. So if you had 100% clay, you'd plot right here. If your soil had 100% silt, you'd plot over here. And if you're at the beach, this is where sand would be, 100% sand. So in reality, clay is just plot anywhere. This would be a clay with this would be a soil with a lot of clay. This would be soil with a lot of sand, and this would be one with a lot of silt. perfect mixture would be kind of like in this area. Okay, so this basically describes all the different types of soil. Florida soils would be in this region. Okay, so what controls soil formation? Well, the parent material, the residual soil in the area, that's the bedrock that's breaking down to create the regolith. That's really important. We call soil that forms in situ in the area called residual soil, so it just remains there and slowly forms soil over hundreds of years. And then there are areas on Earth that receive a lot of transported soil, and so soil may be forming in upland areas and then is eroded away and carried by water and then deposited in like a river valley, a low-lying area. And so in those low-lying areas, you get a lot of transported soils. Time is really important in terms of the soil formation. It's the amount of time that the soil has to evolve, okay, and become like a good enough soil to support plant life. And soil does take a long time because you need the kind of slow weathering processes to kind of break up the regolith and the mineral matter and deliver kind of minerals to the soil itself so that it can support plant growth. So it's in the order of hundreds of years for soil formation. Climate's very important, although it's a little deceiving. A lot of people kind of wrongly think, or their intuition tells them that, yeah, man, rainforests and tropical areas must have the best soil because the rainforests are just exploding with all kinds of life and green. In fact, soil in the tropics is actually poor, and a lot of the nutrients are found in the plants themselves. Because the tropics rain so much, it's an overload of chemical weathering, and that leaches a lot of the soil of important minerals. So you need a good balance of chemical and physical weathering, and that typically is in latitudes where you have like overnight freezing, so you can have some of that freeze and thaw mechanical weathering break up some of the bedrock in the residual soil. Okay, and then plants and animals influence the soil itself. Here in Florida, we have a lot of areas where there are like pine trees, for example, and palmetto that will grow underneath them. And the pine needles, once they fall off the tree, they become part of the soil. That's some of the organic matter being added to it. But that raises the acidity of the soil because the pine needles are acid-like. So depending on where you are on the earth and what plants are covering that landscape, they're going to have an influence on the soil because that's the organic matter that's going to make up a portion of the soil. Okay. Another important factor is your slope. Steep slopes have very poorly developed soils because they erode very quickly. The best case scenario is flat land or undulating land. Okay, so that's just really slow, gradual hills would be great places for soil to form. And then at high elevations, I'm sorry, not high elevations, high latitudes, when you're closer to the poles, orientation becomes important because if your land is facing one of the poles, for example, it's going to receive less sun, and so that's not as good for soil formation. So here are your examples. You don't get so much soil development in dry areas because of the lack of water. In steep kind of steep slopes, you get no erosion because of erosion, no soil formation because of erosion. Here in low-lying valleys and rivers, you get a lot of transported soils, so we do a lot of agricultural and farming in these areas. And then here, in fact, these are the best areas for soil formation, are areas where it's kind of hilly, slightly undulated land surface, or flat, okay, or really gradual hills. Think of Kansas, okay, that's a really flat-lying area where you have soils develop in situ. Okay, the soil profile refers to the different levels and different layers of the soil beneath the surface under ideal conditions. It's like you know, if you had a cake and you cut out a piece of the cake, you can see the different layers of icing and you know, whatever is in the cake. The soil itself, this is an ideal soil profile. Okay, the topsoil is the O horizon and the A horizon together. Okay, the top layer is the O horizon because this is the area with a lot of partly decayed organic matter. That's how I remember it, O for organic. And then A is the layer with some organic matter, a lot of mineral matter, and this is what supports plant growth. Okay, this topsoil area. Now below the O and A horizon is the E horizon. And in the E horizon, this is the area of alluviation and leaching. So water moving through this will leach out a lot of materials and clays downward to the B horizon. And this is where the accumulation of clay is transported downwards. Okay, so that's that B horizon. Then the C horizon is partially altered parent material. This is the parent material, this is the bedrock. Okay, this is what's breaking down slowly into smaller and smaller pieces, the regolith, and then becoming part of the C horizon. Okay, so here's just kind of a repeat of what I just talked about. So let's compare different soil profiles. This is in Puerto Rico, okay, and here this is in South Dakota. So in Puerto Rico, very hot, very beautiful, great music. Okay, not great soil because it rains so much. The climate has a lot of there's a lot of precipitation, so that water kind of leaches a lot of the important minerals in developing soils, and so makes for an immature soil. And so a lot of times, and especially rainforests as well, when they cut down the rainforest to, you know, have grassland or agriculture farms, it's good for about 2 years, and then you've basically removed all the minerals and important features of the soil for agriculture, and it's essentially useless. Like your crop yields will go down. In South Dakota, there's a good mix of physical or mechanical and chemical weathering, and so you have a very well-developed soil profile. You got the O, A, C, and B. Okay, so how do we classify soils? Well, in the United States, there's a lot of scientists that study soils, and they developed a whole soil taxonomy. There's almost like 11,000 different soils. So here's the major ones, and here's our global soils. See, the ones by the tropics are called oxosoils because they're heavily oxidized. Okay. The good latitudes for agriculture would be in this green area, the mollisols. Okay. And in here. All right, so one of the big issues with soil is that it can erode, and it moves into different areas, especially if a land area is kind of exposed or laid kind of barren before you know, you start planting crops. So the natural rates of soil erosion, this occurs naturally. Humans have kind of exacerbated the problem with our agricultural practices, but it depends on the soil itself, the climate, if the slope of the land, and the type of vegetation that exists. The process that erodes soil, water plays a big role. Rain droplets dislodge soil particles, and then the flowing water carries it away. 2/3 of all U.S. soil undergoes erosion. And the wind does play a role itself in erosion, but usually during droughts. That's when wind plays a bigger role. So the problem with this is that a lot of soil erosion can cause reservoirs to fill up with sediment. That's, you know, we don't, out west, this is a bigger problem because they don't have as much readily available groundwater. They use a lot of surface water, so they dam up a lot of the rivers to create reservoirs. So if you have agricultural areas surrounding it, a lot of that soil can kind of seep into those reservoirs, which can be bad because a lot of times farmers will use pesticides and fertilizers, and that can run through those areas as well. Here you can see in Iowa, there's some rills forming after heavy rain when their farmland's kind of bare. Okay, and then here's a gully cutting through some farmland and creating, you can see kind of soil washing away here. So how do we control soil erosion? Well, don't farm on steep slopes, but if you do, you could do terrace crop planting. In between your crops, put in grassed waterways. I'll show you a picture. And then tree windbreak barriers are good to prevent wind erosion. So I'm sure you've seen this if you've flown around in an airplane. Okay. Right, and you look down and then you can see different farmlands and you see trees that outlines different properties. That's to slow down the wind and prevent wind erosion. Here are those grassed waterways in between kind of cornfields, and you can see that this farmer has got it going on. He or she planted corn kind of to follow the ridges and the elevation of their land, which is a good idea. And so these grassed waterways help catch the soil that may erode from these corn rows. Okay. Here's a close-up view of those grassed waterways. All right, so that's a good way of conserving the soil, and it's in the farmer's best interest. I mean, if they conserve the soil on their land, then they're going to have, great crop yields in the future. Okay, mass wasting is our last topic. This is the downslope movement of rock, regolith, and soil under the influence of gravity. Gravity is essentially the controlling force that will pull this stuff downwards. Please click on that video. It's an amazing mass wasting event. I'll just say it's a lot like, what is that, Final Destination type stuff. Enjoy it. It's pretty cool. Anyways, so mass wasting events can be triggered by specific things. And one is if you saturate this material with water, that can trigger an event from occurring, like a little landslide or a soil flow or a slump or something. And so the reason why this happens is because water's heavy. You ever try to like fill up a Home Depot orange bucket filled with water and then try carrying it? It can get pretty heavy fast. So imagine an area that has been just drenched with water. That water will percolate through all the pore spaces in that soil and regolith and just make it super heavy. So if that's like on an oversteepened slope, the chances of a mass wasting event are increased exponentially. And I'm sure you've noticed this. If you go to the beach, you ever try to build a castle with dry sand? You can't do it, right? It just kind of piles up like this. But if you add a little bit of water, initially water acts as like cohesive material, and then it kind of sticks the sand grains together so you can build a nice sandcastle. But if you oversaturate your sand and water, it's just going to become a sloppy mess over here. And that's the problem. So if you have a lot of water falling down, torrential rains, it gets pretty sloppy and heavy, and that can cause mass wasting events. Another trigger to mass wasting events are over-steepening slopes. What that essentially means is that, like, say you have a mountain or a hill or something, and typically we're like, oh, we want to build a road around this or through it or something. So we start blasting the side of a mountain, and then we create like an artificial wall. That's an over-steepened slope, okay? And that can trigger a mass wasting event because gravity wants to pull that material down into an angle of repose. An angle of repose is like the kind of a stable slope, right? So here you have a bunch of piled up sand. This is the angle of repose. This is the angle at which sand is kind of stable. If you were to add any more sand, it would just kind of roll down this hill and into the bottom. But what we do is we'll just cut this off, and then this would be an over-steepened slope. And eventually, gravity wants to pull this stuff down, so this could collapse. Okay. Another trigger to mass wasting events are the removal of vegetation through forest fire, or perhaps we do it on purpose. doing like controlled blaze or something. But this is especially true like out in California. I recommend going on and just putting up like Highway Hill Fire California, and it's unbelievable. They have brush fires that will just roll across mountains and then just burn all the vegetation on it. And when that happens, like plants, their roots anchor the material, the soil, the regolith in place. So if you burn all the vegetation away, all of a sudden mass wasting can occur at a much higher risk because those things are no longer in place. And to top it all off, California has earthquakes, and if you have any kind of seismic waves moving through the ground, that can also kind of trigger a landslide or a mass wasting event from occurring. Okay, so mass wasting processes are defined by the material that's moving, whether it's debris, whether it's mud saturated in water, if it's earth or rock, and also how the material moves. If it's a free fall of just rock pieces down a slope, is it a slide, like a whole bunch of material slides along a curved surface, or a kind of straight surface, or if it's a flow, meaning that is it a viscous fluid, like saturated in all this material. So here, this would be a free fall of material. This would be a rock slide here. Okay, so these rocks just kind of came tumbling down, and this building heavily damaged as a result. Great spot to have it. We also define mass wasting processes by the rate at which they move. There's fast and there's slow. Here are the two examples on the left. That's a fast landslide, and that blocks the road, and that's a big problem. That sucks, right? And then on the right, that is a slow mass wasting process. Those really, really nice homes close to the looks like there's either a coastline. This looks like a road over here. You see, this is an oversteepened slope, and this material wants to move down because of the force of gravity, and it eventually will. And then those homes are definitely condemned. There's no way that people are allowed to live here anymore. Their yards are just kind of, and the foundations are probably all messed up. That's a shame because those look like really nice houses. Anyways, here's a slump. This is the rapid movement of earth material along a curved surface. So here's that curved surface right there. And this typically occurs along oversteepened slopes, like that GIF example I was showing you. And so what's left behind is you have a scarp, and then also this whole movement here would be called the slump block. Okay, and then the material that was on top, we call that earth flow, which is soil regolith kind of moving downward. Here's another example. This is close to the coastline. Another road. This is in California, Point Fermia. But scarps start to form here, and this material kind of just falls downward, which is pretty dangerous. These are nice homes again. Their yards just go right into the ocean. All right, this is a rock slide. Rock slides are very fast. They're very dangerous. They can damage cars. You can get buried in them. And it's heavy rock material with a lot of mass moving down very fast speeds, so very dangerous. So you can have a surface here rupture, and all this material will move downwards, really high velocities. Okay. Debris flows include a lot of water, so this could be a major like low pressure system or hurricane dumping or storm just dumping a lot of water in an area, and then all this saturated material will come kind of careening down the kind of low-lying valleys and tributaries along elevated areas. This has happened in California as well. After major brush fires, if there's any rains, the rain will carry that material and be saturated. And sometimes, like if you live in areas with a change in slope, this muddy material can kind of rush into your house, and then you've got all this mess inside your house, which is impossible to clean. Okay. In some areas where you have volcanoes, these debris flows can come from volcanoes, and we call those lahars. Earth flow, this is also very rapid. This happens on hillsides in very humid regions. This is when water kind of saturates the soil, and then you get a small little scarp and then some movement here. Okay. Liquefaction also can occur with earth flows. Sometimes they're associated with earthquakes, but it really requires the saturation of water beneath the surface, and then you get some movement here. Creep is the very slow movement of soil and regolith down a steep hill. This has a lot of profound effects on stuff that are around it. It can cause utility poles to tilt, trees to tilt, and fences to kind of spill over. I'll show you a picture in a second. And then one of the last types of mass movement is called solifluction. And that is the movement of material above permafrosted soil. Okay, and they're only active in the summertime, and this typically occurs at really high latitudes. I'll show you a picture in a second. But here's creep. So creep forms in areas where there's a daily freeze and thaw. And so when you have a freeze, you get material expanding, and when you have a thaw, it contracts, and this kind of occurs over and over and over again. And then this material slowly moves downhill. That's why it's called creeping, because it like slowly moves. And so that can cause the bedrock to actually bend as a result of this movement. Okay. And here's the actual example. Here are the bent rock layers. A nice cool picture of it. Here's a sketch of it. If you have a cemetery, those tombstones will be falling over. Trees, their trunks will start to grow curved as a result of that movement. Maybe you received one of those emails that are like, oh, the Bulgarian forest is haunted and all the trees are misshapen like this. Has nothing to do with ghosts or haunted forests or anything like that. That's just a geologic process called creep. Okay, retaining walls. Look at this jerry-rigged retaining wall. They're trying to hold on to dear life before it falls over. But yeah, this stuff is really slowly, millimeters at a time, moving, and it starts breaking retaining walls. You get tilted fences, all kinds of problems. And then here's solifluction. Notice there are no trees. This is an area really high latitude, so it can get very cold in the winter times. In fact, these areas are so cold that they have a permanently frozen part of the ground. It's called permafrost, right? And then only in the summertime does the kind of outer few centimeters thaw, right? And so this area thaws, and it'll move downslope under the influence of gravity on top of the solid section. And what that does is, you can see here, you can kind of see these like almost like as if the landscape's melting downwards. And it kind of is, because the soil and regolith here is mobile because it's warm enough and thaws, and it moves along a solid surface over here.